Can you guys hear me now? Can people hear me now? Yeah, for the YouTube people, for the people who are streaming this on YouTube, can you hear me now? Can somebody write? Okay, cool. I'm sorry for that. So basically, I'll have to state whatever I stated till now because I didn't know that you couldn't hear me. Thank you for pointing that out. Yeah, so firstly, let me apologize for the technical difficulties that I'm facing here. This is the first time I'm streaming, so hopefully you'll forgive me. And yeah, so firstly, the video is horrible. I know that my webcam is not really doing good, but yeah, probably from the next live, we'll sort that out. And audio, I think, is fine. So as long as you can hear me and see the board, whatever you're trying to learn here, you'll be able to do that properly. Yeah. So yeah, and I also apologize for the delay. And yeah, so as I was saying, we'll study Pell's equation today, and uh, people. So people have debated whether it should actually be called Pell's equation because Pell never really solved this equation or studied this equation for the first time. But it's one of those values. It was actually Brahmagupta from India who was the first one to study it, and later Bhaskara also found a solution to it. Real contributions to Pell's equation. But yeah, Pell himself had nothing to do with it, and it's just a miscitation that earned in the name. Anyways, being mathematicians, we won't dwell too much on the history. Let's get into the mathematics. So, as I've written here, this is basically Pell's equation. We are trying to solve this equation x square minus dy squared equals 1, where x and y are integers. Yeah. So x and y are integers. So yeah, d is also an integer. So as I was saying that uh, uh, let's try to solve this when d equals 4. So when d equals 4, how would you guys solve it? So yeah, as someone here pointed out, we can easily factorize this, right? So this just factorizes to x minus 2y into x plus 2y equals 1. And that should be easy to solve, right? Because this is all, everything is over the integers. So if these two product is 1, then x minus 2y has to be plus minus 1, x plus 2y has to be plus minus 1. Those are linear equations. You can easily solve them. So this is fairly trivial. So we are done with this. So this works, this factorization works only when d is a perfect square. So from now on, we will assume that d is not a perfect square. Because if it's a perfect square, then this is very easy and we can just factorize it to solve it. I think my this thing is not working today properly, but anyways. Yeah, so right now we'll be dealing with the solutions of x square minus, we'll try to find the solutions of x square minus dy square. And yeah, so x and y are integers. And yeah, so d is not some perfect square. D is an integer, and d is not equals to some perfect square. So anyways, so how do we solve this? How do we get into solving it? Any ideas? So Mayuk here says something like okay. So yeah, but we want to find what all solutions. Okay, so let's see. Let's try to factorize this anyway. Okay, let's try to factorize this anyway. So yeah, let's factorize this into x minus square root of dy into x plus square root of dy equals 1, right? So we want to find all integers of this form. So right, and this factor, there is something called unique factorization there, and you can just say that x minus root dy equals plus minus 1 if this is true. But this is actually not true in this z root d world. So um, so let's see how things behave in this world. Okay, so what we'll try to do right now is we'll try to study such numbers. Okay, so we'll try to study numbers of the form x plus y root d, where root d is an irrational number, by which I mean that root d is uh, d is not a perfect square, as I already said. So we'll try to study such numbers where x and y belong to z. Okay, and the set of all such numbers is something which we'll call z root d. Okay, so this is basically an extension of the integers, and the integers extended with the square root of d. Yeah, so this is the definition of the set. And yeah, so we'll try to study this set now. While solving these kind of problems where we have square roots and stuff, you must have seen that there is something called a conjugate of every number. So this conjugate is very important in these problems. Okay, we'll see why this is the case later. Basically, these numbers of the forms x plus square root y square root of d, these come as solutions of quadratic equations, right? Of quadratic equations where the coefficients are integers. There the coefficients are not irrational. There the coefficients are integers, and the solutions are basically numbers of this form, right? So that's how root of 2 is basically the solution to x square equals 2, right? So we had rational numbers at first. We saw that no rational number could solve it, and then we said, okay, let this be square root of 2. Yeah. Now what and from this definition of square roots, what naturally comes up is the conjugate, because if you have any quadratic equation, there are two solutions, right? For example, the quadratic equation x square equals 2 has two solutions. One is square root of 2 and one is minus square root of 2, right? Similarly, for the quadratic equation x square equals minus 1, there are two solutions. One is I and one is minus I. Now, can you actually say which is I and which is minus I? You can't. There is an inherent symmetry in this. There are two solutions. They are negatives of each other. And while we are saying that one is I and one is minus I, we are basically breaking the symmetry. Yeah. So we are saying one is plus I, one is minus I. But this symmetry is inherent in the definition. So this symmetry comes up in various places, and that's why this conjugation thing is very important. Okay. So yeah, so what we are going to do is um, we are going to define a conjugate. So when we are studying numbers of the form x plus y root d, we'll say that the conjugate, if this is z, then z bar, which is the conjugate of z, this is red, z bar will be x minus y square root of t. Yeah, yeah. So this is the definition of the conjugate of z. Yeah. Okay. Now from this definition, what do we see? We see that basically we want to find all numbers z such that z times z bar, which is basically x square minus dy square, is 1. We want to find all solutions of this equation, right? So we want to solve this equation. Now, this quantity actually has a name. This z times z bar, this quantity is called the norm of z. We write it as n of z, and what it basically means is the norm. So norm is a certain extension of normal distance. And yeah, for example, if d was -1, and you know, we were working with the square root of -1, which is basically I. So then this ring, or in that case it will become a field. So this set is a ring actually. So there the norm is basically the distance from the origin of the complex number, from for those of you who know complex numbers. So anyways, so basically we are trying to solve this equation, norm of z equals 1. This is Pell's equation. Norm of z equals 1. So we want to find all elements with norm equals 1. Um, Before we try to do that, what we should understand is we should understand some basic properties of norm. And norm again comes from the conjugation operation. So we'll firstly we'll try to understand some properties of the conjugation. Now, one really trivial property, like trivial to prove but very useful, is this. Yeah, so it's this, that the conjugate of z1 z2 is z1 conjugate times z2 conjugate. Yeah. So this is very easy to prove. You can just say that z1 is uh, x1 plus y1 root d, and then similarly z2 is x2 plus y2 root d. And then from the direct definition of conjugate, you can prove this. This is an easy computation. So I'll leave it to you guys to do it. Somebody says he can't hear. Is can you guys hear or not hear? Can somebody confirm that they can hear? Then I'll continue. Okay, okay. So you guys can hear, yeah. Anyways, so from the definition, from easy computation, you guys can check it. So I'll leave it to you guys. So what follows from here? So the conjugation distributes over multiplication, and as norm is basically norm of z1 z2 is basically z1 z2 norm of z1 z2 is z1 z2 times the conjugate of z1 z2, and then as conjugate distributes over multiplication, it follows easily from here that norm also distributes over multiplication. Yeah. So these are all easy to check things. You can easily check it from directly from the definition. So I'm not going to prove this to you. You can keep it as an exercise. Yeah. So yeah, so we found some nice properties of norm and this conjugation. And now let's get back to with this knowledge. Let's get back to Pell's equation. Yeah. So for now, we'll assume that so we were trying to solve this equation: x square minus d y squared equals 1. And if we let z equals x plus root d times y. Okay, my mouse is making a lot of problems today. Let me just fix this. Yeah, if we let z equals this, so this directly translates to this norm of z equals 1. This whiteboard is not working properly at all. Yeah, so okay, so we want to find all z such that norm of z equals 1. For now, let's assume that there is at least one solution to this equation. We'll prove that there is one solution to this equation, but we'll do it at the end of the class. For now, we'll assume that this has at least one solution. And what we are going to see is that if there is one solution, there is actually an infinite number of solutions. And all the solutions are described by a very natural characterization. Okay. So yeah, so suppose we have some solutions. Yeah, and suppose z naught is the smallest solution to this. Okay, and okay, so obviously if x comma y is a solution, minus x minus y will also be a solution. So if z is a solution, minus z will also be a solution. So smallest okay, so what is the norm of x plus root dy is basically the product of z and z conjugate. Yeah, so z is x plus root dy, z conjugate is x minus root dy. So norm is basically this thing, x square minus dy square. So this is just another way of writing it. Okay, so yeah, so actually there will be negative solutions to this also. I mean, if z is a solution, minus z is also a solution trivially. So it makes no sense to talk of the smallest solution, but yeah, we can talk of the smallest solution which is greater than 1. Okay, so if this is non-zero, we can talk of the smallest solution which is greater than 1. My pen is not working suddenly. We can talk of the smallest solution which is greater than 1. This pen is making a lot of problems. Yeah, anyways, so why can we do this? Because actually if z is all a solution, 1 by z is also a solution. Yeah, so because 1 by z is what? 1 by z is basically x minus root dy, because x square minus dy square is just 1. So 1 by z is basically x minus root dy. So 1 by z is z conjugate when we are looking at solutions of the Pell's equation. Okay, so the theorem is this: if z naught is the smallest solution greater than 1, z equals plus minus z naught to the power n. Yeah, so n can be negative also. Yeah, so if n is minus 3, that's just basically means that it's the third power of the conjugate of z. So yeah, so how do we prove this? um, we prove this fairly simply. This is the proof is not that difficult, but I'll show it to you anyways. Okay, not YouTube. So how do we prove this? So let's prove this. Yeah, so um yeah, so suppose z is a solution, so suppose z naught is a solution, then norm of z naught is 1. But that plus minus z naught to the power n is a solution. First we prove that part, then next we'll prove that those are in fact the only solutions. Yeah, so how do you prove that norm of z naught on my plus minus z naught to the power n is 1? How do you prove this? Okay, so this is basically norm of plus minus. Why is pen not working? This internet is causing a lot of problems. Guys, failure. What the hell is this? Norm of this is basically norm of plus minus times norm of z naught to the power n. Now norm of plus 1 or minus 1 is just 1. Not to the power n is what? Basic, because norm is multiplicative, that's just norm of z naught times norm of z naught times so on norm of z naught. Yeah, this is n times. So because norm is multiplicative, we get that norm of plus minus z naught to the power n is just 1. Okay. Yeah, so we have proved that the equation. Now, we will show that these are in fact the only solution. Okay, guys, I'm really sorry, but I think I'm going to switch off the video because otherwise my internet is not really supporting this. Yeah, so just going to switch off my video. Okay, so guys, I'm really sorry, but I had to switch off the video because otherwise this thing is not really working for me. This internet is too slow. Can you guys hear me now at least? Because class is more important. Seeing me is not at all important. Yeah. Can you guys hear me everywhere in YouTube and everywhere? Yeah. Okay. So what we were saying is basically we proved that norm of z naught plus minus z naught to the power n, and we want to show that these are infinite solutions. Um, and this, can you guys hear me? Can I get a yes? Because can you can So norm of plus minus z naught to the power n is 1. We proved this, yeah? Now what we are going to prove is these are infinitely we'll have a solution z to this such that z equals z naught to the power n. Oh my god, this is too difficult. Difficulties here. This is this is too difficult. This is too difficult. Anyways, guys, can we please focus on the class? Anyways, so what I was saying is an increasing sequence with no upper bound. Uh, we so suppose z is not a solution, then we can find n such that this z is between z naught to the power n and z naught to the power n plus 1. And this norm of we suppose not, so this norm of z is 1. So we can find n such that this holds true. Now what this implies is 1 is less than. Now remember that the norm of z naught is 1. Okay, so as the norm of z naught is 1, 1 by z naught is equal to z naught conjugate, as norm of z naught is equal to 1. So yeah, but as the norm is multiplicative, I hope you can see that this norm of this number z times z naught bar to the power n, as it is multiplicative, this will also be 1. But this is a contradiction. This is a contradiction. Why is this a contradiction? Because we assumed that z naught is the smallest solution. Greater than 1. Because we found that z times z naught bar to the power n is in fact greater than 1 but is smaller than z naught. So this is a contradiction. To the power n, and this is working out again. I know that you will not be able to understand anything this is happening. So I guess I'll end today's session. Yeah, I guess I'll end today's session on this note because frankly, I think you guys not understanding anything from this. Yeah. So I'm really sorry to everybody. There's nothing I can do right now. I'll try to, before going live next day, I'll see if my internet can actually support it. If not, then I'll just teach you guys, or I'll figure out something. Yeah. But I'm really sorry to you guys who are attending the class, and I'm also sorry to the people on Facebook and YouTube. But yeah, due to technical difficulties, uh, I think I'll have to end this here. So yeah, goodbye everybody. Because frankly, with this kind of technical setup, it's not like you guys are learning anything out here. So yeah, bye everyone. Have a good day.